The principle of relativity in general isn't a new thing. It boils down to how two people can see the world very differently. But when people say relativity, they usually mean Einstein's theory of relativity, which is a special and mind-blowing case. Like I hopefully convinced you in the last lesson, we've got real experimental proof that at super high speeds, or when measurements are crazy precise, two clocks will tick at different rates, and observers will totally disagree on the length of an object depending on whether they see it moving or not. Those last two things are tough to accept, but they're true. They come from two core principles. All observers, no matter how fast they're moving compared to others, can claim they're the ones standing still. That's not new. We've accepted it since Galileo. The speed of light is the same for everyone, and by less obvious, I mean it sounds crazy. Think about it. If you're sitting on a high-speed train with a kitten in your lap, you'd say the kitten isn't moving. But someone watching from the tracks would say that kitten's flying by at 60 miles per hour. It seems like speeds always depend on your frame of reference, but not light. And we know this is true. We'll get to how later. For now, let's talk about how we measure light speed and what other weirdness comes from this fact. Light is insanely fast, the fastest thing there is. It's 186,000 miles per second, fast enough to circle the Earth 7.5 times in 1 second. I said about because US units aren't exact. In the metric system, it's exactly 299,792,458 meters per second. And that's precise because since 1983, that's how the meter's defined. That level of precision matters to scientists, but it's not crucial for our discussion. For our purposes, we can round the speed of light to about 300 million meters per second, or 300,000 kilometers per second. Measuring something that fast requires special methods. It's completely different from measuring sound, which moves slowly enough that we can easily notice the delay. Consider a baseball game. You see the batter hit the ball in the outfield, then hear the crack of the bat a moment later. Or when you see a jet flying high overhead, but the engine sound seems to come from where the plane was several seconds ago. Sound travels at about 770 miles per hour, just over 1,000 feet per second, which explains why what we see and hear don't match up. If a plane is at 30,000 feet, you'll hear sound coming from where it was 30 seconds earlier. With light, any delay is far too small for humans to perceive. While sound takes a full second to travel 1,000 feet, light covers that distance in just 1/1,000,000th of a second. To measure light speed, you need either extremely precise electronics or very large distances. The first successful measurement used the latter approach. In 1676, Danish astronomer Ole Romer made the first serious attempt by carefully timing the eclipses of Jupiter's moon Io. He recorded exactly when Io disappeared into Jupiter's shadow. This wasn't just theoretical. It had practical applications for navigation, helping sailors determine their position at sea. The connection between accurate timekeeping and determining longitude at sea is fascinating. Reaumur knew Io orbited Jupiter every 42.5 hours, so he could predict when each eclipse should occur. However, his observations didn't match his calculations. Even more puzzling, the discrepancy changed over time depending on the relative positions of Jupiter and Earth in their orbits. Those two positions kept changing. which meant the distance between Jupiter and Earth kept changing too. Through careful measurements and hard thinking, Rømer realized his observations could be explained if light traveled incredibly fast, but still took time to get places. He calculated that light needed about 22 minutes to cross the entire width of Earth's orbit around the Sun. From this, he figured light moved at 220,000 kilometers per second, about 26% slower than we now know it is, but still an amazing calculation for someone working in the 1600s. Those early scientists were seriously smart. Today we could repeat Rømer's experiment more accurately, but we've got better methods now thanks to modern electronics. For example, we can set up two light sensors exactly 1,000 feet apart, fire a laser pulse between them, and measure that it takes about 1/1,000,000th of a second, or use one sensor in a mirror placed far away to do the same thing. 1/1,000,000th of a second seems unbelievably fast, but even a basic modern oscilloscope can measure time periods 1,000 times shorter than that. Measuring light speed is impressive enough, but proving it's the same for everyone no matter how they're moving is even tougher. Let's look at how scientists figured that out. There are two main ways this was determined. 1. The first conclusive proof from the mid-1800s. 2. More modern approaches. The first big breakthrough came when scientists in the 1800s were trying to solve a puzzle. What medium carries light waves? By the early 1800s, Thomas Young had clearly shown light behaves like a wave. Einstein's work on the photoelectric effect wouldn't happen for decades. At that time, everyone accepted light was a wave, but waves need something to travel through. Think about it. Throw a baseball and it flies from your hand to the catcher, but put a rubber duck in a lake and watch waves pass by. The duck mostly bobs up and down without moving toward shore. The wave energy moves, not the water itself. Sound works similarly. Air molecules vibrate back and forth but don't actually travel with the sound. The exact way air molecules move is different from water waves, but that's not what matters here. What's important is that all waves known to 19th century scientists needed some medium, like water or air, to travel through. Another key point is that relativity, the regular 17th century Galilean kind, applies to most waves. For example, if you're on a fast-moving train and yell from one end to the other, you'd measure sound's normal speed. But someone standing at the station would measure a different speed for your yell because the train is moving. Sound speed depends on the medium, and we always measure it relative to when that medium is still. This created a big problem for 1800 scientists because light seemed to travel through empty space. There was no obvious medium. Space appeared completely empty, yet starlight reached Earth just fine. Scientists back then weren't 100% sure space was a vacuum, though they suspected it was. But they knew they could create vacuum chambers by pumping air out of glass containers. Light still passed right through these empty chambers, which raised the question, what's carrying light waves? The proposed solution dated back to the 1600s when scientists were arguing whether light was a wave or particle. Wave supporters suggested an invisible substance called the luminiferous ether, or just ether. This idea actually came from ancient Greek concepts about celestial spheres above Earth. By the 17th to 19th century, some believed this ether filled the entire universe, letting light travel through it. But ether had problems. First, nobody could actually detect it. It might as well have been as imaginary as angels dancing on a pinhead. Second, wave physics suggested a paradox. Generally, waves move fastest through stiff, dense materials. Sound is 17 times faster in steel than air. Since light moves incredibly fast, ether would need to be extremely rigid, yet the universe clearly isn't solid. Ether supporters basically shrugged and called this an unsolved mystery. There was another weird thing about light. The ether posed another big problem for late 19th century scientists. Was the ether moving, or was Earth moving through it? This question became more concrete in the early 1860s when Scottish physicist James Clerk Maxwell compiled previous research into what we now call Maxwell's equations. These equations showed that electric and magnetic fields are interconnected. They're really just two aspects of a single phenomenon called electromagnetism. This was groundbreaking. But the real bombshell came when Maxwell combined his equations using calculus and algebra. His math predicted the existence of electromagnetic waves traveling at the speed of light. This strongly suggested light itself was an electromagnetic wave, though it wasn't absolute proof yet. Einstein's particle theory of light was still decades away. But here's the catch I glossed over earlier. Maxwell's equations said electromagnetic waves move at light speed. But speed relative to what? The obvious answer was, relative to the luminiferous ether. If true, this meant we might measure Earth's motion through the ether. This brings us to 1887. When American physicists Albert Michelson and Edward Morley conducted their famous experiment at what's now Case Western Reserve University in Cleveland, Ohio. Remember from Lesson 3 how Thomas Young passed light through two slits, creating alternating bright-dark spots. Whether spots were bright or dark depended on how the light waves lined up, what physicists call phase shift. When wave peaks aligned, they created bright spots. When peaks met troughs, they canceled out into darkness. Michelson and Morley used similar interference principles. The details of their setup were different, though. First, let me explain their equipment. They started with a light beam aimed at what's called a half-silvered mirror, or beam splitter. This special mirror reflects half the light while letting the other half pass through. You make one by putting a super-thin reflective coating on glass. They positioned this half-silvered mirror at a 45-degree angle to the incoming light. This split the beam in two. Half continued straight through, while the other half reflected off at a right angle. Now they had two light beams traveling perpendicular to each other. Next, they placed two regular mirrors to bounce each beam back toward the half-silvered mirror. When these returning beams hit the splitter again, part of each passed through while part reflected, recombining them onto a viewing screen. This is where the phase interference happens. Depending on whether the beams arrived in sync, peaks aligning, or out of sync, peaks canceling troughs, the screen showed either bright or dark spots. The actual pattern was slightly more complex, but that's the basic principle. Before discussing the light speed aspect, it's important to note how crazy sensitive this setup was. Light's wavelength is under a millionth of a meter. Even microscopic changes in path length would make the pattern flicker between bright and dark. Their equipment could detect vibrations from someone stomping their foot a football field away. To prevent this, they installed everything underground where vibrations were minimal. But even underground wasn't enough. They took an extra step by mounting their whole setup on a massive sandstone block and floating it in a pool of liquid mercury. As you probably know, mercury is extremely toxic, especially dangerous for unborn children. But Michelson and Morley weren't pregnant, and this was the 1880s, long before OSHA existed. I can only imagine what my lab safety committee would say if I proposed this experiment today. The mercury pool served two critical purposes. It dampened vibrations incredibly well and allowed them to smoothly rotate the entire apparatus. This rotation capability was absolutely essential for their experiment. Here's why it mattered. According to mainstream physics at the time, the ether filled the entire universe. But we knew Earth both rotates and orbits the Sun, which itself moves through space, so Earth was probably moving through this ether. You could think of it like an ether wind blowing past Earth. Since their device sent two light beams at 90-degree angles, they could rotate it to align one beam with this hypothetical wind direction while the other stayed perpendicular. If light speed depended on the ether, then the two beams should travel at different speeds through the arms, which would show up as phase differences in the recombined light pattern on their screen. The tricky part: they had no idea which direction this ether wind might be blowing from. The ether was supposedly moving through Earth. But here's the brilliant part of their experiment. By rotating the device, they could align the arms either parallel or perpendicular to this ether flow. Even without knowing the exact direction, they expected to see the light speed difference between arms change during rotation. This should have caused visible shifts in the light-dark pattern on their screen. If they saw these changes, it would prove the ether existed. So what did they find? Drum roll, please. Absolutely nothing. Zero. The light pattern didn't change at all. The only possible explanation? Light speed stayed constant in both arms regardless of orientation. This result essentially killed the ether concept. Now, the ether idea didn't die overnight. Some proposed workarounds, like Earth somehow dragging nearby ether along with it. But Michelson-Morley marked the beginning of the end. Over time, every alternative explanation got disproven, leaving only Einstein's solution. No ether exists, and all observers measure light speed as exactly 299,792 kilometers per second. Physicists use c for this, from the Latin celeritas, meaning speed. Before moving on, here's another rock-solid way we prove light speed is constant for everyone, using particle accelerators, my specialty. First, a slow-motion example. Imagine a pro baseball pitcher throwing 100 miles per hour fastballs. Now put that pitcher on a 100 mile per hour train. Someone trackside would see the ball moving at 200 miles per hour. 100 from the throw plus 100 from the train. Simple. We do this daily with real particle accelerators, not thought experiments. Here's how. We make electrons emit photons, light particles. Then measure light speed by timing how long photons take to travel between two stationary detectors. The result? Always exactly c, no matter how fast the electron was moving when it emitted the light. You simply divide distance by time to get velocity. And it always comes out to 300,000 kilometers per second. Now let's use a particle accelerator to fire electrons at nearly light speed, and I mean crazy close. Old CRT TVs had electrons moving at about 20% light speed, while modern accelerators reach 0.9999999 of light speed. Following the baseball analogy, if an electron moving at near light speed emits light, we'd expect to see the light moving at nearly double speed from our perspective. Common sense says light should reach the detector in half the time the electron takes. But that's not what happens. Both the electron and photon arrive in essentially the same time, meaning the photon always moves at exactly c, whether emitted by a stationary or ultra-fast electron. This only makes sense if light speed is constant for all observers. We've run this experiment at all times of day, year, accounting for Earth's motion. If any ether wind existed, we'd detect speed variations as our accelerator's orientation changes. But we never do. This is ironclad proof that light speed is universal. While counterintuitive, this fact underpins all of special relativity's wild predictions, which experiments consistently confirm. But here's another mind-blowing aspect. Light speed is identical across all frequencies' energies. Unlike bullets where faster means more energetic, a low-energy radio wave and an ultra-high-energy gamma-ray photon both travel at exactly c. We know this thanks to cosmic gamma-ray bursts, GRBS, the universe's most powerful explosions. When GRB 090510 occurred 7.4 billion light-years away, its gamma rays trillions of times more energetic than radio waves arrived within 2 seconds of the radio signals. That's precision of 1 part in 100 quadrillion, equivalent to measuring the 4 light-year distance to Alpha Centauri within 1 foot. This universal speed limit clearly points to something fundamental about reality, though we're still figuring out exactly what. We'll revisit this in Lesson 16 with gravitational waves, which also move at light speed. But first, more fascinating topics await. See you soon.